in physics, in science even, that there is this interplay between theory and theoretical derivations, mathematical theories, and observation, that the relationship between these two is not always entirely straightforward, and there is this process that the community goes through about arguing whether approximations that people make or tools that people make to make calculations about things and predictions are really valid. Now you see this in very general in some of the scientific things that are debated today about climate change, for example, and the effects of climate change, or viruses and how virus spreads. And you see this often in science, that there is this argument between theoretical calculations and data. And I think this gravitational wave observation, this is an example where the approach of just proceeding with the calculations and trying to get some results and push on and not worry about the mathematical niceties turned out to be the right way to do it, and turned out to be very successful. And only after a while did the mathematicians and the people who wanted mathematical rigor manage to sort of catch up and fill in all the holes. Those of you who know something about quantum field theory will maybe know about Haag's theorem. There is this theorem in quantum field theory that basically says the interaction picture in quantum field theory that is used for calculating all of the interactions that are done at particle accelerators to derive everything we know about particle physics and quantum field theory, that this interaction picture mathematically does not exist. The whole structure is based upon things that are mathematically completely inconsistent, and it is therefore somewhat surprising maybe to some people who are very mathematical that the whole thing matches experiments so very, very well. And this maybe is not quite as strong an example as that, but this is also in gravitational waves. We have very clear demonstration, I think, in some ways that nature and sometimes does behave in these almost mathematically inconsistent ways, or at least our understanding of how nature works does not need to be entirely mathematically rigorous to be correct. So that was that. So that then convinced most people that gravitational waves were being emitted by this system, that clearly there was some effect of the gravitational wave emission on the system itself. We didn't see directly the gravitational waves, but we saw the effects of the gravitational waves on the system. And then really the big question for anybody else who was thinking about this as a physicist at least, was whether those gravitational waves could then propagate from places where they were being sourced, where they were being emitted, whether they would then propagate from the sources all the way across space to here on Earth. And there are two things that would possibly prevent that, two main things that theorists could think about that would possibly prevent that. One is you have this gravitational wave propagating across space. It's causing these expansions and contractions. If it passes through a plasma, most of the matter in interstellar medium, intergalactic medium is plasma, is ionized, it's electrons and protons. And as you squash and squeeze such a plasma, you will cause an electromagnetic interaction that maybe transfers energy from the gravitational wave into the plasma, into electromagnetic emission, and basically takes the energy out of the gravitational waves and puts it into light. And theoretically, again, using sort of astrophysicist approximations, people could calculate a mean free path for a gravitational wave moving through a plasma. A mean free path like this, put in values of the proton mass, C, density of interstellar plasma, and you would find that the mean free path was about 10 to the 110 meters, which means that this damping is very, very low for what we expect the interaction to be. So this would suggest that the gravitational waves do not lose very much energy to interstellar plasma as they propagate. The other possibility you could imagine was that there may be some unusual or interesting, shall we say, quantum effects that this gravitational wave propagates, and that there is some interesting quantum field effect from its vacuum polarization as it passes through vacuum space. People looked at this as well, and the argument from Gary Gibbons at least was that any reasonable regularization of the vacuum expectation value of the energy momentum tensor of the gravitational field must vanish, meaning that if the gravitational wave has some effective energy momentum tensor and you evaluate its expectation value in the vacuum, any reasonable way of doing that, which means that there are many ways of doing that, many reasonable ways of doing that, but any reasonable way of doing that suggests that this should vanish and that these things should not cause non-trivial interactions with quantum vacuum. And so that didn't seem to be, at least at a theoretical level, at least at this level of approximation, a problem either. No, this is the effective stress energy tensor of the gravitational wave, considered as a perturbation on top of some background. Yes. Yes. Right. So that brings us now to these three gentlemen and the LIGO observations. So what the LIGO observations demonstrated was that these theoretical arguments for why these gravitational waves should propagate without being diminished in any way, these were reliable. This was now a observational confirmation of these arguments that these effects should not occur. So these guys won the Nobel Prize in 2017 for their decisive contributions to the LIGO detector and the observation of gravitational waves. So the fact that we saw gravitational waves here on Earth is now confirmation, observational confirmation, that not only are they emitted from sources, but they are also able to propagate across space and get here to Earth. So this is what one of the gravitational wave detectors look like. This is the one in Hanford in Washington, in northwest part of the continental United States. There are two arms. Each arm is 4 kilometers long. There are lasers that bounce back and forwards along these arms. And this is the central station where all the fancy optics and the control rooms and things are here in the central station. This project, at least according to an estimate in 2014, has so far cost the National Science Foundation in the United States $620 million US. So this LIGO project is actually the most expensive project that has ever been funded by the National Science Foundation in the United States. It's not as big as some of the projects that are funded by the Department of Energy, but at least for the National Science Foundation, it's the most expensive project that they have ever funded. Okay, so here is my cartoon picture of what is going on in the detectors. The two arms that you see, the 4-kilometer arms, there's one of them there and one of them there. There is a laser source in the building at the center, sends in a laser beam. There is a beam splitter. It splits the beam into two paths. One goes down there, one goes down there. The lasers then bounce off the mirrors. In fact, what they actually do is there are mirrors down here as well, and they bounce backwards and forwards many times down here, and many times down here. But eventually they come back to the beam splitter, and they are recombined. And depending on the relative lengths of these two arms here, you either have constructive or destructive interference here at the beam splitter, and some of the signal is read out onto a photodiode that can tell you whether you have constructive or destructive interference here, and read out in the photodiode here. So the idea is, and again this is the failure of my PDF to do any motion, is if the gravitational wave comes in, it will stretch and expand the space along these lines here, along these arms here, and so it will change the relative length of this Y arm here and this X arm here, and therefore will change whether there is constructive or destructive interference here at the beam splitter, and that is then read out from the photodiode down here. So what we are reading out, the thing that is actually the observable, is the photocurrent falling on the photodiode here. Okay, now this experiment there's a little bit of magic in this experiment. The light that is propagated along the arms has a wavelength of approximately 10 to the minus 6 meters. It's approximately micrometers in wavelength, and yet the changes in length scale that are predicted to occur from these gravitational wave events are at the level of 10 to the minus 19 meters. So the changes in length that you are trying to measure are much, much smaller than the wavelength of the light that you are trying to use to measure them. And this is maybe a little bit surprising at first consideration. On an order of magnitude scale, you would say this is not possible. It's not possible to measure something very, very small with wavelengths that's much, much larger, 13 orders of magnitude larger than what you're trying to measure. And so the magic that occurs is because of the magic of the way that the interferometer works. Basically what the interferometer is measuring is a phase shift between the light in one arm and the light in the other arm. There is a very standard formula from undergraduate physics for interference patterns of such things, that the power that is coming out, that is landing on your photodiode, is a function of the power that is circulating in your arms, the amount of light you have circulating in your interferometer, times this cosine of the phase difference. This phase difference here is the thing that is what is the most important thing for your experimental observation. This pattern here looks like this. So the power that you see coming out on your photodiode, it oscillates between being 0, when this factor here is 0, and being a maximum, full power, all of your light coming out on the photodiode here. It oscillates like this. And the idea is that if you can control your interferometer such that you're always very, very close to this point here, you can actually measure very small displacements away from 0. You can measure the change of your intensity in very small displacements away from 0. So the phase difference here, the sort of separation here, is a function of the wavelength of your light that is into your interferometer. And what you're seeing is not the difference between a minima and a maxima, but actually, if you're very careful, you can measure very small displacements away from the minimum. So that phase difference is given by this formula here. There is a factor 2 pi because one of the beams is reflected and one is transmitted. And then this factor here, which is delta t, the time difference taken to go down one arm relative to the other arm. This lambda here is the wavelength of the light, the actual wavelength of the light. And this b factor here is the number of times that the light bounces backwards and forwards along each arm before it is recombined. Right? So this is all simple undergraduate physics. You take this formula, you stick it in over here, and what you find out is that your displacement sensitivity, this length scale at which you are able to determine, is going like this formula here. Right? So this is the wavelength of your light. You can choose the wavelength of your light to be convenient for your optics and your laser. If you can make this B factor as large as possible, you can drive down this delta L. If you can make this P out as small as possible, keep yourself here near a 0. Make this as small as possible and make the power maximum, the maximum power, the amount of light that you're pumping into the interferometer as large as possible. Then if you can do all that, you can make this displacement sensitivity very, very small. So you can drive this displacement sensitivity actually much lower than the wavelength of the light that you are using in the interferometer. And that is what the experimental challenge is for building these interferometers, is make this B factor as large as possible, have the light bounce back and forth along the arms many, many times, and have the power that is circulating in the interferometer as large as possible, pump as much power into the arms as possible. There's a huge amount of power circulating in the arms, but then very little of it is actually coming out and hitting the photodiode. So that is what you do, and that is how you get from 10 to the minus 6 there to 10 to the minus 19 there. Right. In order to see a signal, you need to be able to distinguish the signal from your noise sources. There are a number of different noise sources that occur in such interferometers. You are bouncing a signal backwards and forwards between the mirrors. So anything that is causing the mirrors to move other than a gravitational wave will be a noise signal. Right? And the mirrors, the way that they are held in place is they are suspended by wires. The wires are connected to the building is connected to the ground. And so every time the ground shakes, it shakes the building, shakes the wires, shakes the mirrors. And you try and dampen out all of that shaking because you're not interested in the movement of the ground. You're interested in the movement of the mirrors due to the gravitational waves. So there is, for example, seismic noise. That is the brown curve here. It's very, very high at low frequencies. So this is the frequency range of your detector. It's very low, very high at low frequencies, less than 10 hertz. Drops off very steeply. There is also quantum noise because your light that is moving around in your detectors is made up of little photons. When the photons come out and hit the photodetector, they're not coming out in a continuous stream. They're coming out one photon at a time. Pop, 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 pop. And this causes quantum noise in your readout. That is the purple line here. There is also suspension thermal noise. So the suspensions, everything is at room temperature. So all the atoms in the suspension and in the mirrors are all moving around with Brownian motion because of their finite temperature. And that is causing things to move as well. And then there are various other noise sources, gravity gradients, things moving outside, the air moving relative to your detector, causing a local gravitational effect, and so on and so on. But the net result of all these different noise sources is this black line here, and this black line here determines what your sensitivity is. And it just so happens, by various miracles, that the peak sensitivity that you get down here at order 100 hertz or a few hundred hertz, your peak sensitivity, the place where you are most sensitive, just happens to be the frequency at which you expect stellar mass black holes and neutron stars to be emitting most of their gravitational wave power. And so this fact that the size of the detector that you can build here on Earth and the technological constraints that come from your ability to pump power into the laser and control the thermal fluctuations of things just happen to coincide or conspire to make yourself most sensitive to neutron stars and stellar mass black holes at the point at which they're emitting most of their gravitational wave radiation. So that is the reason why the thing that we see with these detectors is neutron stars and stellar mass black holes. So this is the theoretical noise curve. This is the thing that the experimentalists look at. This is what they're trying to drive down by improving the technology, push this sensitivity curve down by fixing all of these things or reducing these things as much as possible. This is what it actually looks like, the noise budget. So it has that same shape. It is high at low frequencies, around 10 hertz. It goes up again at high frequencies around 1,000 hertz, and it has peak sensitivity here around 100 hertz, a few hundred hertz. There are various noise sources, lines that appear for various different reasons. This one here, 60 hertz line, this is because everything in the United States is vibrating at 60 hertz because the power, electricity that is supplied to all the computers and all the fans and everything that is powered by electrical mains in the United States is at 60 hertz, and it causes the entire country to vibrate backwards and forwards at 60 hertz. I don't even know what is the frequency here in Korea. Is it 60 hertz in Korea? Yeah. 60 hertz in Korea. Same. Yeah, same in here in Korea. So in Japan, there is this weird thing in Japan that half of Japan is 50 hertz and half is 60 hertz. In Europe, it's 50 hertz. In the United States, it's 60 hertz. But you get this whole vibration and everything because of the electrical main supply. These are the harmonics of that. There are harmonics of this. This thing here, this is the violin line. This is because the suspensions, they are like little wires, and any vibration that is caused will cause basically the wires to vibrate like little violin strings. This will cause a noise source that is quite high at the high frequencies, harmonics of that. And then these guys here, these ones here and these ones here, these are calibration lines that are added by the experimentalists into the detector in order to check how the detector is working and to control its response. So you can actually push on the mirrors by various different ways, either by little electrostatic drives that are attached behind the mirrors, or by firing photons, firing laser light at the mirrors and pushing on the mirrors and making them vibrate ever so slightly. And this is how you check that you are calibrating the actual movement of the mirrors. And it actually is how you show that the whole experimental setup is able to measure these very, very small displacements that you expect from gravitational waves, right? Because you know how light works when you shine light on the mirrors, and you can push on them ever so slightly, and because of these calibrations you can actually check that the whole thing is working like you think it should be. So that is that. In addition to those noise sources, most of which are kind of long duration, they don't change very much with time, or they at least change rather slowly with time. There are a number of unknown noise sources in the detectors. There are things that occur at random times that people don't fully understand where they're coming from. They are known not to be gravitational waves because they only occur in one of the detectors and not at the other detector, so they don't look like they're astrophysical. They're something local. And there are a number of different auxiliary channel sensors that are placed all around the detectors to try and pick up all of the other kind of environmental effects that might affect your measurement, and to understand exactly how the environment is affecting the measurements. So there are accelerometers, microphones, temperature sensors, magnetometers, seismometers, even a cosmic ray detector at Hanford, and so on and so on. These are put all the way around to try and eliminate the possibility that other things other than gravitational waves can somehow be getting into your gravitational wave channel and making something that looks like a gravitational wave. So if you want to make the argument that what LIGO is seeing is not gravitational waves, but is, for example, lightning strikes or earthquakes or voltage fluctuations in the power supply or ocean waves, somehow you have to have a model for how those effects get into the gravitational wave channel but do not show up in all of these things. So one of the things that is a bit surprising for people is that this gravitational wave detectors, they are very, very sensitive. They are designed to be very, very sensitive to gravitational waves, but they are also designed to be not very sensitive to other things like lightning strikes or ground motion or electromagnetic pulses or things like that. And these other detectors here, these are actually more sensitive to those things. So the gravitational wave detectors, they are sensitive to this rocking of the United States backwards and forwards at 60 hertz because of all the electric power. But other things like the seismometers are actually more sensitive to that than the gravitational wave detector. So you can see that more clearly in the seismometers than you can in the gravitational wave detector. So any alternative explanation for the observations has to have an explanation for why it doesn't occur in these things that we think we understand does occur in the gravitational wave channel. Okay, and that then brings us now to the beginning of the astrophysics. So this is at least some of the observations that have been made. These blue things up here are the binary black hole mergers, so two black holes that merge together to produce a third black hole here. The blue ones up here, these are the ones that have been detected by LIGO Virgo collaborations. These purple ones down here, these are some of the black holes that were known or are known because of their electromagnetic emission. Most of these guys, the purple ones, are in our galaxy. They're quite nearby, and we see them mainly by X-rays, or the X-ray emission of the accretion onto the black holes Most of these blue guys, or all of these blue guys, are not in the galaxy. They are far away, and they are different types of sources to these purple ones. They are different events. But these are then the black holes that we know that have stellar masses of roughly the order of stellar mass, or 10 stellar masses, 10 solar masses, or 100 solar masses. These guys down here, these yellow ones down here, these are all the neutron stars that were known or are known by their electromagnetic observation. Again, most of these are in our own Milky Way. They are seen by accretion of gas onto the neutron star again. And this one here, this orange one here, is the binary neutron star system that was observed by LIGO Virgo, the merger of two neutron stars merging together to form what is probably a black hole. If you zoom in on this plot very carefully, you will see there is a little question mark on top of that dot there, because nobody actually really knows what these two neutron stars merge together to form. So that's a sort of summary of the observations that have been made so far. What I'm going to talk to you about now is how you go from the data that you record from your photodiode, or at least from your calibrated output of your photodiode, to that kind of picture, to determining that there are actual gravitational wave events in the data. Okay, so again, these gravitational waves, it's in some sense a completely new sense that we have for determining about the universe. It's not light, we don't see it with our eyes. It's a whole new way of seeing things in the universe. And many people are skeptical that this is even possible, that you can find things without using your eyes. This, for some people, is rather amazing. They are very skeptical of this. And so the process of how you go through this and how you understand this is something that people have thought about a lot. So the task that you have, this data analysis task, is whatever is your data, and this is actually very general, whatever is your data, you have some data, and what you want to do is you want to separate it into bits of your data that have signals in it, things you are interested in, and data that does not have signal in, that just has noise in, that you're not interested in. So you can imagine taking your data and putting some of it in the signal pile and some of it in the no signal pile, in the noise pile, right? And when you do this, whatever you do, there is some chance that you will make a mistake and that you will put some data that does not have a signal in the signal pile, or you will put some data that does have a signal in the no signal pile. There's always a chance you will make a mistake. So what we try and calculate is try and minimize the probability of making a mistake by mis-sorting the data into the wrong pile. So what you do is, whatever your data is, some series of numbers, is you calculate some statistic, some number, you combine those numbers in some way, whatever you want to do, add them all up together, multiply them all together, whatever it is you want to do, compute some statistic, and compare this to a threshold, right? And your threshold is basically some number that determines whether you put it in the signal pile or you put it in the noise pile. If your statistic has a high value, put it in the signal pile. If it has a low value, put it in the noise pile. And whatever you do, there is this probability of making a mistake. So you can ask yourself, how do I minimize the probability of making a mistake? What do I mean by minimizing the probability of making a mistake? And what these guys, the Nyman Pearson guys, came up with is they came up with a criteria for which you would say you are minimizing your probability of making a mistake by maximizing the probability of making a detection. So maximizing your chances of finding a true event ending up in your pile of signals for a fixed probability of putting something that does not have a detection in it in the detection pile at a fixed false alarm rate. So you fix your false alarm rate and then you maximize your probability of making a detection. And this is how you compare all the different choices that you can make for this statistic and find out which one is better. Right? The one that maximizes the probability of making a detection at a given false alarm rate that you choose. And the reason why this is relevant, this is from 1933, so it's a long time ago they came up with this, is that they showed that there is a solution to this problem. There is a way of doing this. There's a optimal statistic for doing that. And what that is that you compute a likelihood ratio, right? This f of x, the optimal choice, is the ratio between the probability of x given your signal hypothesis, whatever your signal hypothesis is, divided by the probability of x given your noise hypothesis. Take that likelihood ratio, compare that to a threshold. Threshold is whatever you want it to be, and that is the optimal thing to do. They showed this mathematically. That is the Nyman-Pearson criteria. That Nyman-Pearson criteria, when it was developed in the 1930s, was developed in the context of frequentist statistics, but it has a very straightforward interpretation in terms of Bayesian statistics. So there are these two statistical ways of thinking about statistics: frequentist statistics, do an experiment many times, count the number of times you get a certain outcome. This is frequentist. And Bayesian statistics, which is really all about controlling your knowledge or your expectations of some outcome, and the probability refers to your knowledge of what is the true state of the system. In the Bayesian interpretation, there is a ratio between the posteriors, the probability of your two hypotheses that you're trying to compare, probability of your signal hypothesis being true relative to the probability of your noise hypothesis being true. That is given by this ratio here, which is exactly the likelihood ratio, that thing there, the thing that came out of the Nyman-Pearson proof, times this prior probability. Your prior belief before you do collect any data, your prior belief that your signal hypothesis is true, that your data contains signal, over your prior belief that your data does not contain any signal, prior the noise hypothesis. Right? And these probabilities in here, these likelihood probabilities, they can be obtained for models that have many parameters by integrating over those parameters with some prior range for those parameters. So this likelihood ratio is exactly what comes out also out of the Bayesian approach. It has very natural interpretation, and it is exactly then this prior odds here that tells you what your threshold should be. Because whether you put something in the data pile or the noise pile will depend on the threshold, and the threshold you should compare your likelihood ratio to is exactly your prior probability, your prior expectation that your data contains a signal rather than noise. So if you are 50-50, you are equal, then these two will be equal, this will be order 1, and then you need to compare that. That just has to be larger than 1 in order for this probability ratio to be larger than 1. Okay, so that's all well and good. That's the theory of how you do this. In real life, there are many limitations to doing this. The theory is worked out in the idealized sense, but you have to apply it to a real sense. So one of the problems with this is you need a parameterized noise model. You need some way of mathematically representing your noise so that you can compute the probability of something occurring in your noise. You need a way of being able to compute how likely it is. For the gravitational wave detectors, this is a problem because you cannot turn off the signal. Once you have the gravitational wave detector on, there is no way of shielding it from gravitational wave events. You cannot put a cap on the lens, you cannot shut the roof, you cannot bury it under a lot of rock and stop the gravitational waves from getting in because the gravitational waves get through everything. So there is no way of just collecting data that is pure noise. You will always have signal in there. You also need a parameterized signal model, so you need a mathematical way of computing how likely it is to have a certain signal. This is also a problem with gravitational waves because you cannot turn on the signals. We cannot, on Earth, generate calibration gravitational wave signals strong enough such that we can inject them, fire them at the detector, and see that the detector is responding correctly or as we expect to a given gravitational wave source. It's just not possible on Earth. We have to wait for the universe to do this. The universe does it whenever the universe wants to, and you cannot control that happening. There is no calibration, gravitational wave source calibration. You can mimic it with photons, you can mimic it by pushing on the mirrors, but you're not directly mimicking it with gravitational waves. For large parameter spaces, this marginalization that you have to do over the parameters, so you run this on a computer. If you have a lot of parameters, this process becomes computationally very expensive as you have to search over all the different parameters and do all these integrals over different parameters. And ultimately, whatever you do, the result that will come out will depend on your prior distributions. So the numbers that come out of your experiment will always depend on some level on your prior assumptions of what you expected would come out of your experiment. And there's just no way of avoiding this. Like this idea that somehow experimental physics is completely divorced from expectations that theorists have or expectations that experimenters have of what they're going to see, this is not true. There is always some effect of this on whatever you do. Right. If you can deal with all those issues, and there are various different ways that people use to deal with all those different issues, hopefully what you expect to see eventually is something that looks like this. So this is the first signal that was seen. This is GW15 and 914. This is time going along, time increasing, frequency coming along here, frequency of the gravitational wave. And what you see is, you see this thing going up in frequency in time. And this is exactly what you expect from gravitational waves. For a binary system that is going around each other, it is losing energy to gravitational waves. It is speeding up. The frequency is increasing. The amplitude is increasing. The amount of gravitational waves is increasing as well. It's getting faster and faster and faster. Frequency going up. And that is exactly what you expect to see. Zoop. And it goes up. And then eventually it stops when the two objects merge together and it dies away again. So this is what we expect to see from gravitational waves. And this is exactly what was seen for 15914, the first event. 15914 was a very loud event. I think everybody, experimentalists, theorists, everybody was a little bit surprised that the first event was so loud. It was so loud that you could basically see it in the data like this. Right? You could see it by eye. Now, the expectation had been before that, at least my expectation before this, was that the first events that we would see, they would be quiet. You would not be able to see them by eye, and they would be a little bit borderline, and we would all sit around and argue constantly about whether there was an event, really an event in the data or not. So now we get to play a little game. There is also a little game that tests how good the projector is and tests how good your eyes are. This here is some data, some noise from the detector. It's the same thing as the previous slide. It's time along the bottom, frequency along here. And in here, I have simulated a signal and added it into the data. Right? So here, you can see very clearly where the signal is. It's very obvious. You can see it by eye. And in here, you get to see if you can see where I have added this signal. Right? I know it is there because I added it by hand. Put it in by computer. I know it is there. Right? You're looking for the same kind of chirp signal, something that is increasing with frequency in time. It's in there. It's not massively well hidden, but I don't think most people can see where that is by eye. All of this just looks like noise, right? Now, because I have added this signal by hand, what I can do is I can take the signal away again, or I just start with the original data. So what I can do, because this is just a demonstration, is I can take the signal away. Right? This is no signal now. Put the signal back, take the signal away, put the signal back, take it away. Can you see the signal now? The before and after, you might be able to see that around here, something is changing. Yeah? There. Right? Now that is the kind of signal that the methods that we used to find gravitational waves, the computerized methods that we use, has no problem in identifying that signal. Right? If all you were doing was looking at this data by eye, like a human, looking for something like that, there is almost no way you would be able to tell whether you should put this data in the signal pile or in the data pile. And what I'm telling you is the algorithms that we use for determining signals, you can test them on these kind of things with simulations like this, and it has absolute confidence and it should be putting it in the signal pile. Right? This is for the algorithms that we run, this is a very loud signal. Well, very loud. Loud enough that you are very confident it should go in the signal pile. Like that. And the way that this is done is that you need a model of what signal you expect. This is called match filtering. You need a template that tells you what kind of signal you should look for, that tells you you're looking for something that looks like a curve like that. And using that template, you can then rule out all of the other noise things over here, all the other stuff. Say, this doesn't look like what I'm looking for. Using match filtering, you can find very easily this thing. Right? These templates are based on general relativity, what we think is the theory that describes how these objects orbit around each other and emit gravitational waves. There are various different ways of generating these templates, or waveforms as we sometimes call them. Numerical relativity, simulated on a computer, solve the equations on a computer. This will give you, in some sense, the full solution. These guys up here, they're very expensive to run, take a long time to run. There aren't very many of them, so you can't do this a lot, but there are some. What is actually used is one of these two models. One is called the effective one-body model. So the problem is you are trying to solve the two-body problem in general relativity, the motion of two bodies around each other. There is no closed analytical solution to this known in general relativity. So you have to use various approximations to do it. The effective one-body approach, what it does is it takes the two-body problem and then maps it to an equivalent one-body problem that you do know how to solve. We do know how to solve the one-body problem. We don't know how to solve the two-body problem. If you map the two-body problem to a one-body problem, you can solve it, or at least partially solve it. The other method that is used is these IMR phenom methods, and what they do is they take some of the information that we know analytically about this solution, perturbative expansions, and then they match it using kind of stitching algorithms to the partial information that we know from numerical relativity, and then cook it all up in a big phenomenological method to make something that matches at least what we think should be going on. So it's basically interpolating between the small number of points that are known from here and interpolating for all the parameters in between those points. And what you end up with from these models is these little waveforms of these things oscillating in time. You can see that the frequency of this oscillation is increasing in time. The thing is getting louder at the end. This is the motion, the two objects going around each other. It's emitting gravitational waves as it goes round. Each orbit is emitting gravitational waves. It gets bigger and bigger, louder and louder, until they merge together, and then it rings down very quickly and disappears again. These are the models that we use to find these binary systems in the data. And using these models, we are then able to very accurately find the signals in the data. You can test that by simulation. Simulate, test, see if it works, test again, modify, keep going. Okay, so one of the things that these two models here are based on is some partial analytical knowledge of the two-body problem in general relativity. We know in Newtonian gravity how to solve the two-body problem. This is the Keplerian orbits of Kepler. They were known even before Newton came up with Newton's gravity. And by doing a relativistic expansion around the Newtonian orbits, you can get some approximation to what the general relativity solution should be. So you do an expansion in the velocity of these objects. So if the objects are moving very slowly, this should be a good approximation. And as they get faster and faster, it gets less accurate. But you do this expansion in the velocity, and you add terms and expansion in this velocity v over c expansion parameter, and that gives you different what are called post-Newtonian orders. So there is the 0 post-Newtonian orbit, that is just Kepler, that is just Newtonian gravity, no relativistic corrections. Then you add the first power of v over c, that's called 0.5 pn. For historical reasons mainly, this turns out to be 0 in general relativity anyway. Next order, v over c squared, you add that in. This will give you corrections, relativistic corrections. For example, the perihelion precession of Mercury is a 1 pn effect. There are also effects from deviations from general relativity you could add in at that order. And you keep going, 1.5 pn, you start to see spin effects. 2 pn, you get various different quadrupole stuff, magnetic dipole interactions. 3 pn, you get reflections of gravitational waves moving on the background, getting reflected off the curvature, so on and so on. 5 pn is one that's actually very interesting because at 5 pn, effectively at 5 pn in the gravitational wave emission, you start to see the finite size of the objects. You see the effect of the changes in the shapes of the objects due to the fact that they are in a gravitational field. They change their shape ever so slightly, and this affects how they move around each other in general relativity. So this is kind of like a perturbation expansion, and you see that new physics comes in at each of the different orders in the expansions, right? So you have some analytical information, but this is a perturbative expansion. This is not an exact solution of general relativity, it's just a perturbative expansion. But the result of doing all this is there are two different ways of searching for these signals in the data. One is using these models, this match filtering using these templates, and one is a more agnostic approach that doesn't really depend on a model of what you're looking for, but just looks to see if whether your two detectors that you have, whether they have a common signal in them. And both of these methods are used. The one that is agnostic about the sources is this one even. This one here on the left. This is able to see 15.914, but it's able to see it at a relatively low statistical significance because it's not as good at excluding all the background things. But the model searches, those are the most sensitive ones, providing nature is behaving like your model. That is able to find these things at greater than 5 sigma. Right? So there are both unmodeled searches, just with coherent power between the detectors. And then there are also the model searches, template stuff, the match field searches. These ones, if your model is good, these ones will be the most sensitive. In fact, by those mathematical proofs that I mentioned, the Nyman-Pearson criteria, you can actually prove that in some cases, certain cases, these ones will be as good as you can do. You cannot do better than these model template-based searches. Okay, so you might worry that if finding these events is based on models, what if our models are wrong? That is a legitimate concern. That is part of the reason why the unmodeled searches are run, to make sure that we're not missing anything, that we're not accurately modeling. This is an example from 15.914. What you actually calculate, the statistic that you calculate is this thing called SNR, signal to noise ratio. This is the time running along here, and the idea is you're seeing noise, 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 and then blip, your statistic blips up when you see the signal, think there, and then noise, 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 noise afterwards. Right? This is actually the value that was seen of this SNR for the Hanford detector up here. It's a value about 18 was seen, and you can see how clearly it stands out from all the noise. Right? It's so trivial to see that that is not noise or is not part of the distribution of these guys down here. It's clear that it's a blip. That is using the full model. This thing is actually called SEO-BNR v2. That was the model that was used to find the first signal. If you do exactly the same thing, but you ignore all the relativistic corrections, so you literally just take Newtonian gravity, Kepler's orbits for these things, plug them into the Einstein quadrupole formula for emitting gravitational waves, but otherwise just use Newtonian theory. So ignore all these relativistic corrections, all these pin corrections. You get something very similar, noise, 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 and you get a blip. The blip is not as high here. It only goes up to about 14. instead of 18, but you still see very clearly the signal of GW5914. So this means that even if we hadn't developed all of these fancy waveforms and these fancy templates and all this knowledge about relativistic corrections, we would still have found GW5914 with high probability as an event in the data. It was that loud. Right? For things that are quieter, these models are more important, but for the first signal that we saw, it was so loud that it didn't make any difference. Once you have this expansion, this perturbative expansion, you can calculate what the coefficients of the expansion are in general relativity at 0.5 order, 1 pn, 1.5 pn, and this then becomes something that you can compare to your data to see whether the values of those coefficients match the predicted values in general relativity. And this is something that was done for GW5914. So these are the PN orders going along here, starting at 0 PN. This is the Newtonian case, adding these relativistic corrections, V over C, as you go along. This is their deviation from the GR value. Right? And these are the data points that were seen for 5914. And you can see that this is relatively flat here, along here. And the reason is because GW5914 is so relativistic that this V over C parameter is of order 1. And it means you are almost as sensitive to the higher order relativistic corrections as you are to the lower order relativistic corrections. This is what you can do with gravitational waves. What was known beforehand was stuff based on just pulsars. Pulsars are much wider apart. Their velocities are much lower. The V over C parameter is much lower. It's 10 to the minus 4 instead of order 1. And so you are much more sensitive to the Newtonian part than you are to the relativistic corrections, and this goes up much more steeply. So you know nothing really about what these guys are here. And now with the gravitational wave events, we are able to constrain these higher order relativistic corrections much more accurately. So all the new physics that comes in up here, we can now constrain it much better with gravitational waves than we could previously with the pulsar observations. In terms of the astrophysics for these events, before any events were seen, astrophysicists spent a lot of time trying to work out how many events we would be able to see. So running models of how stars form, evolve in binaries, come together, interact with each other, get close enough to merge, and then merge, how often this happens in galaxies, how many galaxies you will see. And back in 2010, the LIGO collaboration published this paper where they tried to show what the rates would be for various different types of sources. Neutron star binaries here, neutron star black hole binaries, binary black holes here. And they had different rates. They had what they called a realistic rate, what they supposedly thought was the realistic rate, the best guess of what the rate would be here in the middle. Then there was a low rate, pessimistic rate they thought would, if nature behaved like that, it would be unlucky, and a high rate. If nature behaved like that, it would be great, but probably the rate should be somewhere between the low and the high. And you can see the different rates here for the different events here. This is what was known in 2010 based on all this astrophysical modeling. Lots of different choices go into those models. There's lots of uncertainties in those models, lots of parameters you can tweak. That's why the ranges of these guys were quite high, 3 orders of magnitude here for the neutron stars, even more than that for the black holes. Now that we see observations, now that we start to collect data, we now start to measure that rate. And so we start to constrain the parameters that go into these models and tell us more about the astrophysics and start to constrain some of those parameters and narrow the uncertainties on them. So that is what is done now that we start to see rates, start to see events. So now you can start to build up a noise model of what is the noise actually measured in your detector. So this is the noise that is measured in the detector against some statistic. This happens to be a likelihood value here. You see how the noise drops off very, very steeply. This is the number of events. So this is the probability of seeing some noise statistic down here, the probability of seeing it. You see it drops off very sharply in the noise statistic. Now you start to see events. You can have a signal model You can actually use the fact that you see things to calculate how often they're occurring and build a signal model, and then you can start to ask the question of were certain events so loud that we were lucky to see them, or are they just sitting in the distribution of things that we expect to see going on anyway? And that is what is shown here for various different events. These two guys, they sit pretty much in the signal model. This 150914 was kind of an outlier. It was actually louder than you would expect it to be, given that what we now understand, we were lucky to see this guy here. Right? But now it's now based on a data-inspired understanding of what the rate of these events are. And you can see how the noise drops off much more steeply than the signal. And this is why things transition very quickly from being almost certainly ending up in the noise pile to now almost certainly ending up in the signal pile. Right? The transition between those is very, very sharp. And the reason for that is because these two slopes have very different slopes. Okay, so now once you start doing observations, you start to learn about what the rate is. You start to understand what the actual rate is. You can start to build this likelihood ratio for how likely something that you see is to be a signal, and put it in the signal pile. And this is what is done nowadays, and they calculate what is called P-astro, which is basically this probability of being astrophysical, or the probability that you should put it in the noise pile or in the signal pile, this number here. And you can see that there are various different events here, all with P-astros greater than 0.999. They're in the signal pile, and they're almost certainly signals. And you go down, and this P-astro, it then changes very quickly from being some number that is almost certainly 1 or very close to 1 to being number that is less than a half. And these guys down here, these are probably noise events. Right? Transitions very quickly. These ones up here are all events that have been seen and claimed by the LIGO collaboration. The 1,000 or so people who get first look at the data and get first chance to claim whether there are signals or not. Some members here in the audience. These ones in red here, these are events that have now been found by groups outside of the LIGO collaboration who have taken the data that LIGO has made public and run their own algorithms on it and found new events that were not found or not claimed by the LIGO collaboration. So you change your statistics slightly, you change your method slightly, you go through the process of calculating probability of being astrophysical, and now these other groups, there's a group from Princeton, there's a group in Germany, who now start finding events that they think are actual events that are not claimed by the LIGO collaboration. In particular, there's one here that has a probability, astrophysical probability of greater than 0.99 here of being an event. Right? So there is still development work going on in designing these statistics to take your data, crunch the numbers, and decide whether to put it in the signal pile or the data pile. There is still active development work going on, and different groups get slightly different answers, although now the Princeton group and the Germany group at least agree at the level of these ones in red, so these three guys here. This one down here is only 0.7, probably 0.7 of being signals, so you could argue about that, but this one probably is unarguable. Okay, so that is what we are learning. I'm going to talk quickly about the binary neutron star system. The binary neutron star system is now the most studied transient event in the history of astronomy. Everybody who has a telescope of any kind, gamma rays, X-rays, ultraviolet, radio, whatever, has pointed at some point to that part in the sky where it occurred. This is a table of all the observations that were made at the time. There was an optical counterpart found in the optical. People could see that there was a spot that appeared that hadn't been there before. So there was a lot of confidence that this was identified as the source of these gravitational waves for this binary neutron star system. There was a whole lot of fun about the localization of this region. So various different detectors. This is a gamma ray detector here. This purple one is the Fermi gamma ray detector, sky location for the gamma ray burst that they saw, quite big. And then you see that the gravitational waves were able to reduce that down to this green area. The green area was just what you would see from where it occurred in the sky, just from the gravitational waves. And then it was found, the optical counterpart was found at the star inside, exactly inside where the gravitational waves should be. There was this stonking great big glitch in the Lewison's detector at the time that it occurred. This is one of these noise sources that people try to remove, but it's a noise source that only occurred in Lewiston, didn't occur in Hanford. This one was a relatively easy one to deal with because some of these other auxiliary channels were also able to pick this up, and you're able to subtract this from the data. And humans are able to see very easily that there is a track behind this line here. But the algorithms that were running at the time basically were confused by this, and this was just vetoed by the algorithms, which is why it took a while to get the alert out. Let's not get into that too much. You were able to do a lot of interesting science with this binary neutron star system. For example, measure the luminosity distance to the source relatively accurately. Not that accurately, but plus minus 25% or something, 40 megaparsecs. The nice thing about it was that the realistic rate that was projected in 2010 was 1,000 events per gigaparsec cube per year in a range 3 orders of magnitude. This was now measured to be almost exactly what the realistic rate was predicted to be in 2010. With the luminosity distance, you can infer a value of the Hubble constant. It's not accurate enough to distinguish between various different arguments about what the Hubble parameter should be, but it's getting there. And a very nice thing that was able to do is the fact that you see photons coming from this event and you see gravitational waves coming from this event means that you can time race the photons against the gravitational waves and determine the difference in speed of the gravitational waves and the photons to 1 part in 10 to the minus 15. And the first time anybody's ever been able to say that accurately, that gravity propagates at the same speed as light. There was also evidence of heavy elements being produced by this binary neutron star. So you have the binary neutron stars come around, they get close enough together, they get ripped apart by the gravitational forces. There are lots of neutrons flying around, all these neutrons collide with each other, they produce heavy elements, and it is now believed that the majority of the heavy elements, including things like gold, are predominantly produced by merging neutron stars. So most of these guys that are heavy elements down here, the orange ones, uranium down here as well, they are believed to be predominantly generated by mergers of neutron stars. There are a number of other potential gravitational wave sources. So we have seen mergers of 2 black holes. We have seen 1 merger of 2 neutron stars. You can have systems where 1 is a neutron star, 1 is a black hole. This has been observed. It was observed in 2019. The LIGO collaboration has not reported on this yet in any detail, but I expect that some information is coming out about it imminently. I know nothing about it. There are people in this room who know much more about it than I do, but it is coming soon. There are other things that you might see, so single isolated neutron stars, deformed rotating galactic supernovae, intermediate mass black holes, various astrophysical backgrounds, stuff to do with cosmology. Basically, the probability of observing these things is going down as you go down the list. None of these things, at least to my knowledge, have been observed yet, but may be observed in the future. This is the network as it stands. These are the 2 detectors in the United States. They are currently on. As I checked this morning, they are running. They are currently on. This is the one in Italy, the Virgo detector. It is also on currently. This one, Livingston, is currently the most sensitive one. Virgo is the least sensitive one. There's one coming in Cagra. They are hoping to come and start taking astrophysical observations at the end of this year. And then there is one proved to be constructed, is starting to be constructed in India. This is the plot of the various expectations of how we are going to go forward into the future. So this is the year going forward. We are here, 2020. LIGO, the American detectors, Virgo, the Italian detector, Cagra, the Japanese detector. We are at 2020. This plot is already out of date because these guys are still running in this 03. So this is still going on. And these guys, the Japanese, are hoping to join the party sometime later this year. The experimentalists work hard. They push down the sensitivity. This is where the original LIGO detectors were. This is where we are now, heading towards this sensitivity down here, this orange and these green ones with the advanced detectors. There are plans in the future to go further than this with upgrades, and then maybe in the future build something like the Einstein telescope that gets even lower, and we just generally push the sensitivity further down, get more and more sensitive. The more sensitive you get, the more region of space you can see, the more events you can see, the more things you can see, the more things you can learn about the events you do see. So the experimental sensitivity is getting better and projected to get better as we go forward. There is actually a full spectrum of gravitational waves, just like there is for light. So this is the frequency here, the gravitational waves. The LIGO detectors are around here. So as I explained, here on Earth, just so happens that the thing that you can build tends to have a peak sensitivity around 100 hertz. This corresponds to things like neutron stars and stellar mass black holes. If you put things in space, for example, LISA mission, you can get sensitivities around 10 to the minus 4, 10 to the minus 3. Then you will be sensitive to things like supermassive black holes, very big black holes in the center of galaxies, and various other things. You can even use pulsars in the galaxy as basically effectively your arms of your interferometer. So they have an effective length of the size of the galaxy. The detector is effectively the size of the galaxy, and that will be sensitive to things that have wavelengths of approximately the size of the galaxy, so very, very long wavelengths, and that can go all the way down to things like stochastic background, these pulsar timing arrays down there. So all of these, this is coming, 2030 or so. These guys, they have every chance of seeing, they are taking data now, tracking these pulsars. They could see a signal any day now. That's a bunch of references. Slides are available somewhere probably if you want to look at it. That is the end.
Any question?
No. I have a question. No.
I have a question about detection mechanism of interparameter experiment. Usually it is explained that the gravitational wave deforms the length of arm.
Yep.
But the frequency of the gravitational wave is about 100 hertz, right? And
yep.
I expect that the plasma frequency, I don't know, how to say, the interaction rate of these particles composing this arm material for experimental setup is that interaction rate is much higher. So similarly to the case of star systems, do not experience much about the expansion rate of the universe in a short lifetime. These arms experience the gravitational wave adiabatically. So I thought that this interference pattern is not due to the change of arm length, but helped by the photon oscillation of redshift, blueshift, redshift, blueshift by the passing of the gravitational.
Yes, that is that is a consistent interpretation of what is happening. My argument would be that there is actually a gauge choice in how you interpret what the experiment is actually doing, depending on how you choose your gauge or your understanding of the time. Basically, what you are really measuring, the thing that you are really measuring, is this phase difference, right? And that phase difference you can interpret either as the frequency changing in the arms and everything coming back together at the same time, or you can interpret it as the arms are actually moving and they're changing in length, and things are taking longer to travel along the arms. That, I would argue, is actually a gauge choice ultimately, rather than something that you can determine by experiment which one of those is happening. So it is consistent to have both interpretations. And what you actually measure is this phase. This is the gauge invariant thing that you actually measure. How you interpret that is sort of open to your choice of gauge.
Any other questions? I have two questions. First of all, a detector, can we think that detector is some free-falling object?
So the mirrors that the light is bouncing backwards and forwards between, they are free to move in the, longitudinal direction. They're not really free falling because they're hanging by strings. So they're not free falling totally, but they are free to move in the longitudinal direction. So in that sense, they are free falling in the longitudinal direction. The idea is the mirrors will be free falling, but everything else around them, the tubes, are not free falling.
And for the sensitivity of the gravitational wave, the quantum noise, I think that is most important for high frequency.
Yes. Well, actually, here in this region here, so this is a theoretical prediction based on models, but here in this region here, it is still actually the dominant thing that is producing this. So from even at frequencies around 20 hertz, it is actually the quantum noise that is dominating. But then, well, actually, it's the main contribution. It's not all of it, but the main contribution. And then at high frequencies around 1,000 hertz, basically all of the noise is the quantum noise.
So then, could you explain why some 100 hertz is most
Why is 100 hertz the most sensitive part?
It says safe from the quantum noise.
So there are a few constraints that constrain this. One of the constraints is the length of the arms that you can realistically build on Earth, which is a few kilometers, basically. That limits part of it. Another thing that limits it is the background of seismic noise here on Earth. A lot of that is human-induced, created by humans, but it is also created by waves and earthquakes and things like this propagating on the Earth. So it has scales associated with human activity, whatever the scale is, human activity, and the scale of the Earth. And that is picking up this brown one here, which is dominating here at 1 hertz, sort of 10 hertz and below. And then what is limiting this here is the amount of power, laser light, that you can pump into the laser arm without melting the optics. So you need to have mirror coatings on the mirrors that can reflect the light and don't absorb very much of the energy. What actually happens is they absorb some of the energy and they heat up. But if you try and pump more energy into the arms, the mirrors will basically either catch fire or melt. And so you need to keep that energy under control, and that is now the limit that limits how much power you can put in, which then limits this quantum noise here. And the combination of those two, basically the brown one and the purple one, their peak just happens to be at 100 hertz.
How much you can adjust this minimum point?
Not very much, less than order of magnitude.
For the initial LIGO, I remember the sensitive frequencies around 1000 hertz, not few hundred.
Ready?
For the initial LIGO.
Do I have a plot of that? I thought I had a plot of that.
Yeah, so you can see the sensitivity noise curves combined. There.
Here. This one? This dark blue one here.
That's initial
100 hertz.
100.
Virgo a little bit more, but still 200 hertz maybe.
What is the black one?
Black one, Geo.
That's Geo.
So Geo, because the arms are shorter, right? Because the field is the size it is. It doesn't have very good frequency at the low frequency, but because you can still pump as much laser light into it, it still has almost the same sensitivity at the high frequencies.
But I remember the people expected the most probable source is binary neutron star models, and the frequency about the merging time is around kilohertz.
Yes.
Right. So I guess the initial design was made for that case. So this most sensitive frequency was much higher than 200.
So I wasn't around when the initial designs were being made, but as you say, if you have two neutron stars, 1.4 solar masses each, then the loudest that signal will be is down here somewhere in kilohertz range. And my understanding at least is that this design here, if you had literally just tuned it to be sensitive to that, you would want it to be there, the bucket, right? And that is not possible. So people did not do that. They did the best they could to do that, but the best they could do to do that is here in the 100 hertz range, and that just happens to be the frequency of the black hole mergers. But if people could have, I think probably they would have built it so that it was peaking down there. Because that would be the thing that would optimize your ability to see neutron stars. Right? So the reason why it is this shape is not because there was a deliberate design choice to target a certain source. It's this shape because that is the limitation that the size of the Earth and the optics puts on you.
Any other question?
So this Einstein telescope would be, like I'm just confused, is it the space telescope?
No. The Einstein telescope is a European project to build a underground detector with 3 arms, so it's actually a triangle rather than 2 arms. It'll be underground, it'll be cryogenically cooled. They don't yet have funding for it. They have funding for the design, and hopefully it will get approved by the Europeans to run sometime in the 2030s, to run at the same time as LISA.
So LISA is the space one?
Yes, LISA is the space one. So LISA sensitivity is over here somewhere at 10 to the minus 4. Okay. Like this. Yeah, so all those things here, they're all the ground-based ones down here somewhere. LISA is this one. So LISA, the arm lengths are millions of kilometers long.
So I'm just curious. So the LISA one is it's almost like a satellite. It's like maybe.
It is a satellite. 3 satellites.
Satellite, right? So what is the extent that the distance can be made?
So it's 3 satellites. So the arms are the distance between the satellites.
Yeah.
So the limitations for that are your ability to keep that arm length roughly constant and not have the satellites wander off and move away from each other.
So is it that's the upper limit that you can put?
Yes, that is limiting. So it's the arm length, the separation of the LISA satellites, that is limiting its sensitivity at the low frequencies. And that is because you put them in orbit around the sun. That is, I mean, it's probably not as cheap as putting it in orbit around the Earth, but it's the cheapest place you can put it into orbit. If you could put it way out into space, you could make the arm length anything you like, but that orbit wouldn't be very cheap to put it there. You also have limits on the laser that you can. I mean, the laser spot gets really, really big by the time it goes from one satellite to the other.
So I would like to know the spin measurement of these black holes, what the LIGO has detected. So what kind of spin you actually measure? So these are mostly curved black holes, right?
This is my personal version of this for some of the initial events. So the ones that are produced after the mergers, they are likely to be quite high spin. So this is the curve parameter here, from 0 minimum to 1 maximum. The ones that are the results of the mergers are quite likely to be quite highly spinning, 0.7 or something. The ones that are observed before the mergers, the individual spins on the black holes are quite uncertain. You see the error bars are basically the entire range. But the combination of those spins is constrained to actually be quite close to 0. The mass-weighted combination of those spins is quite likely to be close to 0. So either one is spinning down and one is spinning up, and they match off, or the spins are aligned in the plane, in which case the net spin in the orbital direction is basically 0, or the magnitudes are 0. Now, if you only have one event, it's difficult to tell which one it is. But once you start measuring this multiple times, the probability that all of them are forming like that, or all of them are forming like that, I think for astrophysical reasons goes down, and the probability that they are like that, 0 magnitude each, goes up. So I think what we are seeing, although we are not directly sensitive to the individual spins, what we are seeing is actually the magnitudes of all these guys are actually quite low.
There was this little bit controversy whether these are real black holes, because whether you can produce black holes at some 80 solar mass. So the spin measurement of the initial black holes becomes very important to understand what they are actually. So do you have
From the formation channels.
Yes.
Yes. So if you take two non-spinning black holes and you allow them to evolve in a binary, then theory predicts that the final black hole you will end up with will have quite a high spin. So if you want to form quite heavy black holes from mergers of black holes, you would expect that those black holes that you form will have quite high spins. And what I'm saying is the ones that we are observing so far, the evidence is pointing to, at least on average, that they are on average of low spin magnitude, which suggests they are not on average being formed from mergers.
Okay, we are quite behind the schedule, so and we let us have 10 minutes of break.